Welcome to the video. Here I'll show you how to calculate the equivalent resistance for a complex type of circuit given here. We know that in series you add the resistances together to get the equivalent resistance, while in parallel you add the reciprocal of the respective resistances together to get the reciprocal of the equivalent resistance. However, neither of those are going to work here because, as we can see, the resistors are neither in series nor in parallel. So how do we approach this problem? As you know, this circuit is only consisting of only resistors here and here. So we know that resistors are linear component. By that, we can see that the circuit AB exhibits a linear behavior, which means according to Ohm's law, we know that V is equals to IR. So in this circuit, if a equivalent resistance exists, we can see that the applied voltage into the circuit AB is equals to I times the equivalent resistance. So how do we calculate the equivalent resistance? First, we know that if you apply any voltage of V1, we will get a current going through the circuit I1. Again, if you apply any voltage of V2, we will get a current of I2 going into the circuit. So therefore, we can see that regardless of what voltage you apply into the circuit, we'll get a respective current going into the circuit while maintaining the same equivalent resistance into the circuit. So using this information that we know so far, we can apply a voltage into the circuit, let's say 10 volts. It can be any applied voltage. You can apply any voltage, 5 volts, 20 volts, 30 volts, just for the sake of conveniences. And for the sake of ease of calculations, I have applied a 10 volt in the circuit. So how to approach the problem? First, we know that according to the Kirchhoff's current law, the KCL law, we know that the current going into a junction is equals to the current that is going out of the junction. So in this circuit, let's say a current is going here, I1, I2, I3, 4, 5. You can assume the direction of I3 in any direction. If the final calculations show negative, then you can simply flip the arrow on the other side. So first, and also we can name this portion the potential Vx, and let's name this Vy. So let's use this portion of the circuit for our primary calculations. You can see, so according to, let's name it L1, the first calculations. So we can see that according to the circuit and the KCL law, I1 is going into the junction, while I3 and I4 are going out of the junction. Therefore, I1 is equals to I3 plus I4. So I1, let's name it 10. I1, how do you calculate I1? 10 minus Vx by 9. I3 is Vx is Vy, I3 plus Vx by 7. Skip some space here. Okay, okay, let's isolate the Vx and Vy. Let's name Vy as the subject of the equation. So Vy by 3 equals to x by 3 plus Vx by 9 plus Vx by 7.5 minus 10 by 9. So final calculations using the calculator. Vy is equals to 26 by 15 Vx minus 10 by 9. So we have a linear equation, which is L1. So we can use another portion of the circuit, which is this, get L2. So you can see the currents that are going into the junction is I2 and I3. The current that is going out of the junction is I4. Sorry, I5. So I2 is 10 minus Vy, 6 plus 3 is X minus Vy, 2 equals to Vy by 3.5. Let's isolate the Vx and Vy. So our final calculation of Vx so it's 33 by 14 Vy minus 10 by 2. Oh, wait, it's 5. Okay, so we have two equations here, L2 and L1. We can simply substitute one of them into the equation to get our Vy and Vx, which we can use to find I1. Use these two equations to get I1 and I2. If we add them together, we get the equivalent current. Okay, so far we know the Vy and Vx equation. Let's simply apply the equations into the circuit. Okay, so Vy is equals to 26 by 15 times. We know that Vx is 33 by 14. Vy is 5 minus 10 by. Okay, so y is equals to 3 by 35 Vy minus 6 by 3 instead of 9. Y. So we have Vy as 770 by 242 or 3.16 volts. So how to find, let's find Vx. So Vx is 333 by 14 times 770 by 243 minus 5. So Vx is 200 by 81 volt or 2.46 or 2.47 volts. Okay, so we know Vx and Vy. So let's find I1. Here. How to find I1? I1 is equals to 10 minus Vx by 9. So 10 minus 10 minus 200 by 51. Note that I'm using the fractions into the calculations for more accurate results. So 610 by 9. Actually milliamps. Jeez. I2 is equals to 10 minus Vy. X. Okay, so we have our final results of I1 and I2. So the equivalent current going to the circuit equals to I1 plus I2. So 160 by 51 milliamps or simply 1.9. So using this information, and finally calculate the equivalent resistance going into the circuit. So the applied voltage is 10 volts, and the current going into the circuit is 16 volts. That is 1 by 16 kilo ohm, or simply 5.0625 kilo ohm. This is the final result and the final answer problem. Note, again, you can apply any voltages like 20 volt, 30 volt, or 5 volt, and you will always get the same answer, 81 by 16 or 5.0625 kilo ohms. You should give it a try using different applied voltages to confirm the answer. Thank you. And if you have any questions, note, comment down below and I'll try my best to answer them. Thank you.